Welcome to Lecture 7. This is a continuation. It's the second part of our lecture on why is it warming. And we're going to begin with a little bit of a summary of where we've been. And then mostly in this section, we're going to focus on fossil fuel burning and the generation of coal, oil, and gas, which create the possibility of a rather large improvement in mankind's ability to have wealth on the planet during the Industrial Revolution. So let me share the screen and get you started on this. So we're back to why is it warming, and we have been through. I should start by congratulating you for reaching this part of the course. We've been through a lot of details, and started out talking about the basic ideas behind how the climate works. We created a little bit of vocabulary and some idea of mechanisms. And hopefully that was useful for you when we got into the question of is it warming, and then why is it warming where we are right now. And what I would like to do is summarize a little bit. I'm unfortunately going to do this by reading you something, which may not be what you tuned in for, but you can skip it if it's not, if it doesn't go over well. But here's the basic, here's what I'd like to do. Because we've been over a lot of ground, we want to talk about what is the basic logic behind answering these questions. Why is it warming? And I should say, is it warming and why is it warming? And it seems reasonable in any debate to ask for the simplest possible logic trail that attempts to prove the assertion that I have an answer to this question. This, of course, leaves out a lot of details, graphics, data, mathematics that show detailed evidence. And the loss in this approach is that it puts limits on the observer in terms of ability to judge supporting propositions that got us to that conclusion or assertion. The advantage is the clarity gained by distilling the sequence of inferences and their connections and the data into a few thoughts that hopefully reach a conclusion without distractions associated with this and that detail. So since we've been through a lot of details, I thought this was an appropriate point to get down to that kind of level of logic for these two questions. So let me just read this. To the question of is it warming, we measure the increase in surface temperature directly. Both the troposphere and the first 1,000 foot of the ocean show increased temperatures. The measured changes are both fast, 2 degrees Fahrenheit in 100 years, compared to historical ice age changes, 2 degrees Fahrenheit in 1,000 years, and significant. A 2 degree Fahrenheit change compares to a total 10 degree Fahrenheit change for glacial to interglacial ice age temperature changes. While the direct instrument temperatures are statistically challenging to assemble when producing a global temperature trend, there are many other indications of warming that are easier to measure. These include total energy in the top 1,000 meters of the ocean, the melting of the cryosphere, the increase in global mean sea level, and the slow but steady adjustment in plant and animal life consistent with warming. So that is kind of the bare bones logic, leaving out all the little details that we went through. Now let's do the same thing for the question, why is it warming? Both in the instrument data of the last 50 years and in ice core and ocean sediment data, 2 different data sets, actually in total 3 different data sets, atmospheric concentrations of CO2 are highly correlated with temperature. Any theory to explain warming must also explain the coincident CO2 changes. We also note the greenhouse effect caused by various gases, but principally CO2, about 75% due to CO2, raised the Earth's temperature from 0 degrees Fahrenheit to about 60 degrees Fahrenheit. Models of key factors that influence the climate indicate the largest contribution to warming is caused by greenhouse gases, together with the feedback effect of increased moisture in the atmosphere. Global circulation models that include effects of the biosphere, the cryosphere, and the carbon cycle, as well as atmospheric and ocean circulation, can simulate current temperature trends as well as other more detailed climate effects, including temperature changes with latitude. These models also indicate the primary role of greenhouse gases in warming. The source of the increased concentration of CO2 has to be from plant and animal material based on carbon isotope data. A basic mass balance study shows that the quantity of material needed must be coming from plants buried over millions of years and burned for energy in the industrial age. The last two sentences in that paragraph is what we're about to study, the carbon isotope data that shows that this is plant and animal material that's increasing CO2 in the atmosphere, and that there's a large amount of it, and it comes from buried material. So we're going to do that in a minute. But I wanted to read that whole thing to you because it gives you a feeling for what is the logic trail behind our assertion that global warming is strongly influenced by the amount of fossil fuels that we are burning. So that's the story. Now, the logic trail for why it's warming is clearly more complicated than the logic trail for is it warming. This is not because the evidence for greenhouse gas as a primary cause is not convincing, at least in my mind it's not. You need to make that decision yourself, of course, as a listener. It is because we insist on knowing how big all the other influences are by comparison. In other words, aerosols, land use, solar intensity changes, all that. And because we want to predict the size of the greenhouse effect so that we can not just confirm its cause, but also provide a prediction of the future. Both of these desires on our part need to be done in a complex system. The climate system is a very complex system that circulates energy to the poles, has a very, very interesting carbon cycle, and has other effects like albedo changes and moisture changes and so on that we've talked about. So what makes it a complicated question is that the system we're studying is complicated. So that's kind of my summary of that. I congratulate you for getting this far in the course. I realize I'm probably not the most exciting speaker that you've ever heard, or maybe not even close. And I also thank you for taking the time to do it, because I think that it would be nice in a world. I like to convince people that this is at least a question that's important enough that everybody should understand it, at least at some level. So what I would like to do now is move on to the second part of the why is the Earth warming, where we're going to go from the general idea of greenhouse gases down to fossil fuel burning and try and make the logical leap, or not a leap, hopefully, try to provide a couple pieces of evidence that in the greenhouse gases, a principal component of them is fossil fuel burning. There are other components, of course, other things we're doing that influence warming. It's not just one thing, but a very predominant thing, a thing that provides more than the majority of the warming cause is fossil fuel burning. We need to know this because if we ask ourselves, fossil fuel burning has had a huge influence on our wealth of the last couple hundred years, the prosperity of humans on the earth. It's been a remarkable and a miraculous sort of contribution to change. And it's allowed us to grow in population and in culture and comfort. And now the question is this great boon leading to a great problem, and how soon and how fast, right? So that's why we need to ask that question. Now, I'm going to read you a little story as well before we dive into some more data. And this is a story of Carl the Carbon Atom. Starts out, I am Carl the Carbon Atom. I am currently floating in the Gulf of Mexico with 1 hydrogen and 3 oxygen atoms. You call us bicarbonate. How I got here is quite a story. Many years ago, I was part of a cell structure in an amoeba. An amoeba is a single-cell animal that floats around in the water. Many of the amoeba around us got eaten by other floaters, but our amoeba survived until it died. We sank into the very deep ocean and fell into mud particles and other dead animals. The water was so deep there was no oxygen to cleanse us, so we became a stinking, muddy mess. Then we started sinking very slowly, at no more than a few meters every million years. With other stinky stuff over the top of us, we got very packed together and it was getting quite hot. Someplace around 4,000 meters down, I started connecting up with hydrogen and other carbon atoms, and soon became an assemblage that looked like 36 carbons and 74 hydrogen atoms. I do have a thing for hydrogen atoms. They're so generous with their electrons. We became a source rock. Perhaps 40 million years had passed since I was part of that floater on the surface of the ocean. I soon incorporated into a drop of oil with other collections of carbon and hydrogen atoms of different sizes called hydrocarbons. We may have sank a bit further, but I recall the pressure being so high that we began to find cracks and pores, and suddenly we headed off through a sandstone to higher elevations. The sandstone was like a highway headed back towards the surface. We were migrating. Suddenly we came to a stop, pinned against a large dome of salt with no pores to work our way through. We were trapped. One day there was a large rushing, and we started a journey through many pipes until I ended up in a distillation tank and became gasoline. There, 8 of us carbons tagged up with 18 hydrogen atoms. Sometime later, I found myself in the gas tank of a Buick on I-75 South in Florida. After a white-hot bang, I became a carbon dioxide molecule in the atmosphere, yours truly, and 2 oxygen atoms. I probably spent 100 years floating in the clouds until I dissolved back into the Gulf of Mexico, where I am today. So that's the story of Carl. Now, what Carl is obviously doing is he is participating in the carbon cycle on the Earth. He just happens to go through a couple of possibilities in that cycle. He could have been part of a tree. He could be part of a plant. He could have been buried in, he could have been part of a sedimentary rock. He could have been part of a coral reef. He could have been subsumed at a continental boundary into the mantle of the Earth and stored there for millions and millions of years. But this was his recent experience as told to us. The reason I read that is because I don't have a whole series of slides here about the carbon cycle. I wanted you to appreciate some of it before we start down this path of talking about fossil fuels. So let's begin here. This section is about CO2 and fossil fuels. You recognize this picture. This is the warming by place on the Earth. One of the questions of that whole carbon cycle is, if we are contributing to it, which we surely are contributing some amount to it by burning fossil fuels, we understand that there's other sources of CO2. We breathe CO2 out, for example. Plants absorb CO2 when they grow, and so on, right? So we understand that there's other sources of CO2 out there, and there are other sinks. The ocean, CO2 gets dissolved in the ocean. For example, we know the ocean has become more acidic over time. You've probably heard about that, and so on. So how do we measure how much we're contributing and how much nature is contributing? And so we have a way to get at that. We have a way to get at that measurement. It's a little indirect. So think about this. We can do a mass balance. And I've got a little equation here. It says the natural emissions of CO2 into the atmosphere. So how much nature is putting out into the atmosphere, plus the CO2 created by fossil burning, that's the amount we are putting out, has to equal the natural sinks, so the amount that's being absorbed, plus absorbed by plants, absorbed by the ocean, whatever, plus the measured amount of CO2 in the atmosphere. So in other words, the stuff that's left, right, in the atmosphere as you put stuff in and take stuff out, right? Now, that equation seems fairly obvious if you think about it. You can rearrange it. And what we're trying to do when we rearrange this is we're trying to get all of the things we measure on the right-hand side. So we can do something like this. We can say, let's leave the natural emissions of CO2 on the left, but let's bring the natural sinks over. So we're going to, in a sense, this left-hand side measures emissions minus sinks. So it says if emissions are greater than sinks, that this is natural emissions, not anything we do. This side will be positive. This will be positive. If it's if sinks are greater than emissions, it'll be negative. Then on the right-hand side, we'll put the things we measure. So we measure the amount of CO2 in the atmosphere. You've heard about that. That's sometimes called the Keeling curve. And when I say last month we had 413 parts per million of CO2 in the atmosphere, that's measured at several places on the Earth's surface, although it started to be measured. The famous measurement is in Hawaii, where Keeling worked. At any rate, we measure the amount of CO2 in the atmosphere. And it's well mixed in the atmosphere. It does come from sources all over the place, but the atmosphere mixes it because of circulation pretty well. So that number is very representative. Now, that's the amount that's there. And the other piece of the equation is we brought over the CO2 created by fossil fuel burning. And you might say, how do we measure that? Well, we can tell pretty accurately how much fossil fuel of every type we have used in the last year. So we can do this equation annually, but we can tell that pretty much. So the right-hand side of the equation is measured, and it turns out it's negative. So what that says is the natural sinks, the oceans and the biosphere and so on, are capturing more of what we are adding by burning fuels than the natural sources are contributing to the atmosphere, right? So we're actually putting more CO2 into the atmosphere than the measured amount, than the amount that is measured, the increases, right? And that tells us that nature is fortunately, nature is absorbing a lot of this. Now, we kind of know this. In fact, what we know is about 30 to 40% of the CO2 that comes from human activity, principally burning fossil fuels, is absorbed by the atmosphere, by the ocean. That represents about 24 million tons of carbon a day. This is a major sink, and the oceans have been holding back global climate change in a very real way. And we'll later in the course talk about what would happen if their ability to do so changes over time. And so that's a risk we're taking. Now, let me say a little bit about how fossil fuels are formed. Fossil fuels are basically called fossil because they come from ancient solar energy that was collected principally by plants through photosynthesis or by animals who ate the plants. So the plants did the first step and then the animals do the second step, right? Digesting plants as carbohydrates and growing, and then of course they die. In order for it to form a fossil fuel, the plant, the debris, the dead animal or the dead plant has to be sort of separated from oxygen pretty quickly. If it just decays on the surface, the decay is basically like a slow burning and creates CO2. But a lot of these decays happen in an anoxic environment. In other words, environment without oxygen. And then they end up heading in the direction of fossil fuels. So fossil fuels become part of sedimentary rocks. So there may be many large giant plants. There used to be a time before the dinosaurs when there were huge trees, not anything like we have today, almost tree-like, but huge trees and massive forests. And when they did come apart, they basically became kind of coal deposits. There's so much sedimentary load there. And coal, the things that made coal, like the big swamps and places like those, the rock itself that was formed from this decaying material would be very high percentage organic material, maybe 60, 70, 80% organic material. Unlike oil and gas, which would be a much smaller percentage of material. And so these plants and animals, let's stay with the plants for a second. They would form a substance called kerogen, and this is formed mostly of woody trees and ferns and things like that, buried in the ground. And the first stage, depending on the temperature that the rock went through in its history, subsurface history, it could produce peat or lignite, coal, and anthracite. As the temperature, if it went deeper, it would go through that sequence towards anthracite as the final thing. Anthracite is like the cleanest coal you can find. It's not clean in any sense. And coal is kind of a mess. It's got everything in it. All kinds of chemicals, arsenic and sulfur and lots of other chemicals. In a sense, it's a buried melange of organic material that goes through some temperature cycling. Oil and gas are a little different. They get buried deeper, go through higher pressure and temperature ranges. The highest temperature ranges end up with gas, and then there are various kinds, grades of oil that happen. So this, for example, is a picture of a technique called reflection seismology used for exploration. It has a survey ship with a source of sound source, basically a air gun that creates a bubble in the water that collapses and makes a sound wave, goes down through the rocks of layer at different boundaries of these rocks where there's a big change in what's called the acoustic impedance. But at any rate, the rock's density and things like that change the way the sound wave moves through the rock. You get a reflection off that boundary, off the change, that comes back to the surface, towards the surface, and is collected by these things called hydrophones. You basically think of a microphone that's listening for the sound wave coming back. It's all digitized, and you can image these layers through this process called reflection seismology. I particularly wanted to show this to you just so you saw down below how this porous rock reservoir, so there was some place where there was a source rock, which is where the rock in which the material, the organic material, was captured and proceeded to be depressed down into the subsurface, going through various pressure temperature changes. And then somehow the material, the subsequent precursors to oil and gas would move through this source rock into a porous rock where it's stored. In other words, this porous rock has a lot of vugs in it, a lot of holes in it where you can store gas and oil and water. And you can see here the blue, the green, and the orange. The gas sits at the highest boundary, the oil at the next highest, separated from the water, which is below it. And the idea is these materials move through that reservoir rock until they get caught in a trap someplace where the sandstone that's the reservoir, if it's sandstone, the reservoir rock basically pinches out or runs out against a fault or some kind of geologic object that doesn't let this stuff move any further. If there was a way out, it would just escape to the surface, right? And so this is how it forms and how it. So there's a process in exploration for these things called generation, migration, accumulation. The idea is that the oil and gas is generated by basically the motion through the subsurface, the heat and the temperature and so on, the chemical changes, and then it migrates through a porous rock to a trap and accumulates there. And then when humans find it with their technology, they drill a hole down and try and pull it out so they can do things with it. All right, well, now we get to a wonderful graph, only because it's such a great measurement and tells us a lot. And so the question, of course, is, as we saw earlier, the mass balance suggests that the natural sinks and sources the sinks are actually outcompeting the sources, and there is a large contribution coming from burning fossil fuels. But how can we verify that even more? Well, the way we're going to do that is to note that if you look at this graph, and this is another graph of two axis graph, two vertical axes. So along the bottom is the time from 1991 to 2006. On the left side is the atmospheric concentration of CO2, and this is just CO2, not CO2 equivalent, just CO2. And what you see is what's called the Keeling curve, the rise of CO2 since 1991. So you can see in 1991, there was maybe 355, and in 2006, there was a number about 375 to 80, okay? And the actual Keeling curve is the bumpy curve, the sinusoidal looking curve. There's a smooth line through it, and it shows a steady increase. And as I mentioned to you, today's number is more like 413 parts per million. That's what it was averaged in December 2019. So that's what you see in the, I guess it's a rose color or sharp pink or whatever you think that color is. Then you will see another curve on here, and it's got a funny symbol on the axis. So the axis to the right is called the delta 13 carbon ratio. The delta is a very interesting symbol there, and it's got a strange 0 over 2 zeros. You don't need to know what that all is. Just say it's a funny way that scientists keep track of this. But basically what it is back to carbon fractionation. We used this trick before in our during the paleo climate discussion with oxygen and hydrogen isotopes. This is with carbon isotopes. Carbon has several isotopes. The most prominent is carbon-12. You may have heard of carbon-14 used for carbon dating. That's a radioactive isotope. Carbon-13 is another isotope. And it turns out that plants like to, let me back up a second. The curve at the top, the bumpy curve at the top, is the carbon-13 to carbon-12 ratio, okay? So basically what this shows is as CO2's concentration in the atmosphere has gone up, the carbon-13 to carbon-12 ratio has gone down. And why is that? Well, it turns out plants like to synthesize using carbon-12. They preferentially would like to synthesize using carbon-12. Again, this gets back to carbon-12 being lighter than carbon-13. Without getting into the details of the biology of that, the point is that as plants decompose, they give back that predominantly carbon-12 signature, right? I say predominant, I want to be careful. They give back a richer carbon-12 signature. So as CO2 is going up here, you're getting the amount of 13 to 12 going down, saying the CO2 that's going up is going up with a larger carbon-12 enrichment, meaning that it's plant material, right? Now, we would guess this because we would guess from our mass balance that we're putting more carbon in the atmosphere from burning fossil fuels, and fossil fuels are predominantly plants, our plants, right? Or digested plants, one or the other, both of which have enriched carbon-12 relative to the general carbon-12 to 13 ratio. What's even more interesting about this graph is the bumps. So if you look at the leftmost brown vertical line that's sticking up, it says the lowest CO2 level each year. So I should say that these bumps on the CO2 curve, so if you just look at CO2 concentration, you'll notice that there are bumps, and each bump is the bottom, the valley, is when CO2 is being consumed, when carbon dioxide is being consumed more heavily than at the peak, and that is basically North American summer. So in North American summer, the thing about the Keeling curve is the reason that it's bumpy is because in North American summer, plants are alive, they're sucking up CO2, so you get a little bump in the CO2 curve. Even though the average keeps going up, you get a bump in the summer. And in the winter, you get a pulse upward because the plant leaves decay, and you get this little peak upward in the in the CO2 concentration. So if you look up at the 13 to 12 ratio, when you get the plants growing and taking carbon out of the atmosphere, it turns out they're taking out more 12 than 13. And the 13 to 12 ratio, coincident with that point, actually goes up. So there's this 13 to 12 says, oh, you're taking more 12 out, so 13 to 12 goes up. The same occurs in the other direction. During North American winter, when the CO2 curve concentration has a peak in it, the 13 to 12 ratio has a valley, right? Because so that's what you're looking at with this curve. So in some sense, you have a confirmation of the experiment and within the experiment, which is a nice thing to see. The bottom line is there's a confirmation that this material that's being put in the atmosphere has its origins in plants, which of course the energy for that was provided by the sun. And that is a very important step in what we're learning. Now, we want to talk about one more factor before we end this discussion of why the Earth is warming, and that has to do with CO2 in the atmosphere. We in an earlier discussion we talked about a spike in carbon content of the atmosphere way back in the Paleocene Eocene boundary, called the Paleocene Eocene thermal maximum, the PETM, if you want to say that. And we talked about the decay of that carbon spike took 100,000 years. And you might have asked yourself, probably did, why did it take so long? And because you might say, yeah, we're putting this CO2 in the atmosphere, but won't Mother Nature just take care of this for us, right? And I think I talked a little bit about this before. And this is a picture of the way nature takes care of the excess CO2. And this is actually sometimes called the weathering thermostat. The idea is, let's say you have way over to the left, you have a volcano that emits a lot of CO2, or a series of volcanoes close together that emit a lot of CO2. They warm the earth. The earth, as a consequence, puts more puts more water into the atmosphere, because we know that's going to happen. And the rain washes CO2 out of the atmosphere and basically dumps it on the continents where there is exposed rocks. Typically, those rocks are going to be, a lot of them are going to be granitic, because you have volcanoes and various kinds of igneous rocks, right? Basalts and granites, rocks like that. When that CO2 is rained out, the rain together with the erosion of the rock, the rain freezing, the water freezing and unfreezing and cracking the rock open, creates a weathering phenomenon, which if you look at the equation on the right, it shows, I'm putting there calcium, silicon, and 3 oxygens as a representative rock, right? Now, there are other components in there, but those are important components. They combine with CO2 and the erosion action of the wind and the rain and so on and so forth to make 2 kinds of sedimentary rocks, a calcium carbonate rock and a silicon dioxide rock. And that process is called weathering. Those rivers wash create those sedimentary rocks. The erosion and the water running through the continents create those sedimentary rocks usually at the shore boundary. You get deltas, you get all kinds of rock formation. And the oceanic crust, when it reaches the continental boundary, in some cases, basically pushes a subduction zone to swallow a lot of that crust, either oceanic crust or river deltaic crust, whatever. All these sedimentary rocks can be subsumed into the mantle, where they can be stored for a long time. This absorbs carbon. This process basically absorbs carbon out of the atmosphere. And this process can go the other way, where the subsumed sedimentary rocks get metamorphized or changed into igneous rocks plus various gases like CO2 by basically being exposed to the hot, high-pressure mantle, making new minerals, basically igneous rocks. And if those rocks traverse over a hot spot in the mantle, particularly hot spot, you can have a volcano. That volcano will eject the igneous rocks in a semi-liquid, semi-solid form and the CO2 back into the atmosphere. Now, returning to weathering, given today's volcanic activity and in terms of rain and the igneous rocks exposed on the surface of the earth, it's estimated that we would get something like 0.4 gigatons per year, or we have happenings about 4.4 gigatons per year of carbon that's taken out of the atmosphere. Considering we put in 50 gigatons every year, that's not a lot. And in particular, if you use that number, you would say it would take about 70 years to take out 1 ppm of carbon CO2 concentration. So you can see this is a very slow process that we're looking at here. Now, there are other processes that take out CO2, as we've said, the biosphere and the oceans. And we know that those processes are running along at a much higher rate than the 0.1 gigaton per year. But they have some ability to do this, and we know that at some point that ability may not be as good. It may grow for a bit, but it may not be as good as it once was. And we'll get into that later on in the course about where we think that's going. What that means, and this is probably one of the most important graphics of the course. In fact, if there were a final exam, this would be on it. And I want to explain this quickly because we're going to do it again later when we start talking about why we're worried about this problem. But basically, we emit about 50 gigatons per year of CO2 equivalent, right? And that includes all the greenhouse gases. This is a very round number, by the way. It varies year to year. It's a very round number. About 22 gigatons of that 50 end up in the atmosphere. The biosphere absorbs about 15. So you see that there's a Charlie Brown tree in the drawing there, and it's showing an exchange. It is also emitting carbon dioxide when it decays, when its leaves decay, let's say, but it absorbs some carbon dioxide, and it absorbs more than it emits. Turns out, the biosphere as a whole. So it absorbs about 15 of the 50, and currently the oceans absorb about 13 of the 50. Now these are very round numbers. They vary all over the place, right? And let's say the mantle is taking care of 0.4 gigatons per year for us, right? These are annual numbers, all annual numbers. Now, at 280 ppm, at that time, it's estimated there were about 2,100 gigatons of CO2 equivalent in the atmosphere, right? And at 400 ppm, which is roughly where we are today, there's about 3,000 gigatons in the atmosphere. So 280, I put that on there because that's back when we first entered the Holocene, right? And was there for most of the Holocene until the last couple hundred years. We have put in roughly 1,000 gigatons in the last couple hundred years. We have about 1,000 gigatons to go before to get to doubling at 560 ppm. And the reason I use doubling is because you remember we're sort of saying round numbers. We think doubling CO2 from where we were at the beginning of the Holocene will result in sort of a 2-degree centigrade change since the start of the Industrial Revolution. The band there, the little candy stripe band or barber pole band, is the uncertainty, and a rough estimate of the uncertainty in that number, right? Where we might reach 2 degrees. Now, we add about 2 to 3 ppm CO2 equivalent each year. So if you look at that number, you would say, when are we going to get to 2 degrees centigrade? Well, sometime, again, there's a lot of uncertainties here, but sometime between, let's say, 2060 and 2080, we would reach 2 degrees centigrade. It turns out scientists believe that 2 degrees centigrade is a good goal for us to keep to reduce risk. It's not without cost. Reaching 2 degrees centigrade will create some very real problems on the surface of the Earth, but it does help prevent risk of tipping points, things that could get very serious if we don't limit ourselves to the temperature increase that's out there. Now, the prediction of all these things, concentrations and temperature, we'll talk a little bit more about in the next section. A lot of this has to do with what we are going to do, as well as how good the models are. But the point of this simple model is to illustrate that the problem we're talking about is not about flows in and flows out. It's really that we have a persistent atmospheric inventory of carbon dioxide, if you want to say carbon in general, just because of the CO2 equivalent, but carbon dioxide in particular. That is, it is like we're filling up a tank. And it's not as if when we stop, if we suddenly stop burning fossil fuels, the tank would still have that much carbon in it, right? Let me expand on that just a bit. You might look at the graph and say, well, wouldn't the ocean and the biosphere continue to absorb a total of 28 gigatons per year, even if we shut the input off? In other words, let's say tomorrow we were able to just take the 50 gigatons per year and make it a very small number, like 1 or 2 or 3. So suddenly we weren't putting it in. And you would get, in theory, if the biosphere and the ocean kept going at 28 gigatons, the fact that the mantle absorbs maybe 0.1 to 0.4, let's say 0.4 gigatons per year, is not the important sink. The other two things would be the big sink. And if you had to go down 1,000 gigatons of carbon in the atmosphere, presumably the CO2 part of it, let's say it's all 28 absorbed CO2, that part of it would go down in 40 or 50 years, right? Doesn't seem like that's a problem. But what we need to understand is that the biosphere in the ocean is in dynamic equilibrium with the atmosphere. And what that means is that if you turn off the input, in a sense, we're forcing some of that. And you can see that or kind of understand that in the realization that the ocean is getting more and more acidic. So if you turned off the input, in some sense, the ocean would try and equilibrate back. So as you tried to go down in the atmospheric carbon, the ocean would presumably stop taking as much in and get rid of some of its own carbon back into the atmosphere. And this would especially be the case if you got the surface to start to cool, but even without that, there would be some equilibration. So the idea of the 0.4 gigaton per year into the mantle is, if you want to think about that, that might be viewed as we know that is kind of a minimum reduction. You'll get some help from the biosphere, maybe some help from the ocean, but we can't count on the 28 gigatons. And the thing about the mantle is it takes it out. The sequestering of carbon in the mantle takes it out of circulation for a very long time. What goes in the ocean or what goes in the biosphere are still part of the carbon cycle. They're part of the active carbon cycle. So things go up and down there depending on the atmosphere and what else is going on the continents. And so that's why, in some sense, that is still in the system. That amount of carbon is still in the carbon system. And that's why we say it's a tank with a small hole, the small hole being the subduction into the mantle. So over the long period of time, what we know is Mother Nature uses that subduction into the mantle based on increased weathering to try and control, if you want to put some intent into Mother Nature, try and control the amount of carbon in the atmosphere. And that is called the weathering thermostat, as I've said before. Or if I didn't, I'm saying it now. So that's kind of a little further explanation. And I think it's fair to say, at first, we would get some help from the ocean and the biosphere, but it's totally unclear how long that would last. And we know that it won't last forever. It won't even last too long, because those bodies, those reservoirs of carbon are going to respond in such a way that they won't be taking as much carbon up. So it doesn't go away quickly. It's going to stay there for a very long time. And what that means is that any changes we make today, or as soon as we can, will help us in the future. If we let this tank continue to fill, we're running out of space where we will not, where we're going to have troubles with our temperature, and it'll be difficult to backtrack. It'll become very hard to prevent ourselves from going up in temperature. All right, and this is sometimes called the carbon budget of the Earth. It's sort of a way of looking at this and saying, how much do we have left in our pocket to spend before we get to 2 degrees? Now, you could set the limit higher, and in the next section, we'll talk a little bit about some of the repercussions of reaching 2 degrees, which might tempt you to say, let's not set the limit higher. All right, so that's where we've reached the end of this. I hope this has been a good education for you on these subjects. The next lecture will be about the challenges we anticipate from the warming that at this point, some fraction of which is unavoidable. But we will see what challenges we face and what we've got in front of us. Thank you.